Welcome to part 2 of the acids and bases lecture. In this section, we will look at what are strong and weak acids, self-ionization and the ionic product of water, and the pH scale. In the earlier section, we looked at what acids and bases are. But I'm sure you've also heard of strong and weak acids or strong and weak bases. What determines whether an acid is strong or weak? Strong acids are completely dissociated into ions in aqueous solutions. If we look at the acid dissociation reaction, we see a forward arrow. This tells us that the forward reaction is much more favored and the backward reaction almost does not occur. Some examples of strong acids are HCl, HNO3, and H2SO4. On the other hand, for weak acids, the backward reaction is actually more favored. When a weak acid is dissolved in water, it is not completely ionized, so the solution contains a mixture of undissociated acid and dissociated ions. Some examples of weak acids are formic acid, phosphoric acid, and hydrogen sulfide. As you can see, the acid dissociation reaction shows a reversible arrow. Now, please take note that strong and concentrated have different meanings. If we compare 1 mole per dm cube of HCl versus 2 moles per dm cube of acetic acid, which is more concentrated? For concentration, we would compare the molarity. So, 2 moles per dm cube of acetic acid would be more concentrated compared to 1 mole per dm cube of HCl. But if we were to ask which is a stronger acid, then HCl is a stronger acid because it is completely dissociated in water, whereas acetic acid does not completely dissociate in water. As we saw in the earlier section, water is amphoteric, meaning it can act as either an acid or a base. Since water can act as an acid or a base, water molecules can also transfer protons among themselves to a very small extent. Take a look at this equation. 2 water molecules can react among themselves to form H3O plus and OH minus. Previously, in the previous chapter, you have learned about equilibrium and equilibrium constant. The equilibrium constant for this reaction is the concentration of H3O plus times the concentration of OH minus divided by the concentration of H2O squared. But remember that H2O is a pure liquid and should not be included in the equilibrium constant. So the equilibrium constant for the self-ionization of water is concentration of H3O plus times concentration of OH minus, which is this equation over here. This is also known as the ionic product of water. Since this equilibrium constant is specific to water, it is written as Kw. W stands for water. At 298 Kelvin or 25 degrees Celsius, the equilibrium concentrations of H3O plus and OH minus in pure water are 1 times 10 to the power of negative 7 molar. This gives us a Kw value of 1 times 10 to the power of negative 14. This is important, so please remember this value. So for a neutral solution at 25 degrees Celsius, the concentration of H3O plus is the same as the concentration of OH minus, which is 1 times 10 to the power of negative 7 molar. Acidic solutions would contain a higher concentration of H3O plus compared to OH minus, whereas basic solutions would contain a higher concentration of OH minus compared to H3O plus. Importantly, in all aqueous solutions, the Kw is 1 times 10 to the power of negative 14. But wait, maybe you're thinking, in an acidic solution, the H3O plus concentration would be higher. How can Kw remain the same? Actually, when H3O plus concentration increases, the OH minus concentration would decrease correspondingly, and the product of H3O times OH minus would remain the same at 1 times 10 to the power of negative 14. To represent how acidic or basic a solution is, we use the pH scale. pH is calculated using the formula negative log H3O plus concentration. For bases, when we have OH minus concentration instead, we can calculate POH, which is negative log OH minus concentration. Pure water at 298 Kelvin contains 1 times 10 to the power of negative 7 molar of H3O plus and 1 times 10 to the power of negative 7 molar of OH minus. So if we calculate the pH and POH of pure water, we get a pH of 7 and a POH of 7. We also note that pH plus POH equals to 14. This equation, pH plus POH equals to 14, is valid not just for pure water but for any aqueous solution at 298 Kelvin. So for basic solutions, you can first calculate the POH and then convert that to pH by taking 14 minus POH. Earlier, we saw that if you are given H3O plus concentration and need to calculate pH, you can use the equation pH equals to negative log H3O plus concentration. But what if you are given a pH value and need to calculate H3O plus concentration? Taking the anti-log of both sides, you will get the equation H3O plus equals to 10 to the power of negative pH. Similarly, if you are given POH value and need to calculate OH minus, you can use the equation OH minus concentration equals to 10 to the power of negative POH. Let's also take a look at the pH scale and how it corresponds with H3O plus concentration. Looking at the table, we can see that every pH difference of 1 actually represents a 10 times difference in H3O plus concentration. For example, changing between pH 7 and pH 8, you would see that actually the difference in H3O plus concentration is a 10 times difference. This figure on the left shows where some common aqueous solutions lie on the pH scale. pH 7 is neutral, anything below pH 7 is acidic, and anything above pH 7 is basic. We don't usually hear about POH because we would convert POH values to pH by taking 14 minus POH using this equation over here. Let's try calculating the pH of a strong acid HCl. Let's say we have a solution of 1 molar HCl. Since HCl completely dissociates to form H3O plus and Cl minus, 1 molar of HCl would give 1 molar of H3O plus ions. Since pH equals to negative log H3O plus concentration, in this case, pH equals to negative log 1, which equals to 0. In this exercise, calculate the pH of the following solutions of strong acids. Press pause to try it yourself, then press play to view the answer. For question A, 0.1 molar of HCl would give you 0.1 molar of H3O plus ions. Therefore, pH equals to negative log 0.1, which gives a pH of 1. For question B, H2SO4 is a diprotic acid which can give away 2 protons. So, 0.001 molar of H2SO4 would actually give 0.002 molar of H3O plus ions. Therefore, pH equals to negative log 0.002, which gives a pH of 2.7.